Good morning. We lost some people, it looks like. What? Oh, there's a bus that's not made it or something? Okay, so I guess they will show up. All right, so I'm assuming that all of you did the homework that was due today. Did you or did you not? How many of you attempted it? Oh, good. And how far did you guys succeed? You have to look at the solutions. Okay. Do you think that it will be helpful for the people who didn't try it or those who actually looked at the solution to go over the solution again just to make sure that you understand things? Okay, perfect. So we will walk through the examples today, so that what I want to do is spend some time just going over the three problems. It will give you some different tricks that are used in EM. Then I'll show you the codes for the two problems, first two problems. The third one I don't really have data to give you. And then remember, there was also this other problem that I gave you, which I wanted you to look at directly maximizing the log likelihood when the data was latent. And we'll go over that as well. So let's start one by one. I'm trying to figure out what to do. Maybe I'll take this with me. It'll be easier for me to see the problems. All right. So let's start with the first one, which is a fairly, it has something very common with the problem that we did or the example that we showed in class, which had to do with, so problem 1, the situation is that x is a random variable which is 0 with probability p, and it's equal to Poisson with rate lambda with probability 1 minus p. So this is what the problem is, and we want to estimate p and lambda. Those are the two parameters that define this problem. So there are two possibilities. Either x, so what is the basic issue here? If this x was just Poisson lambda, life was easy. We would have figured out how to do this. If on the other hand x was 0, life was easy. So what is the issue that's causing a problem? So for example, if this was -1 and Poisson lambda, would there be a problem? Would I have to worry about it at all? If x was equal to -1 with probability p, or x was equal to Poisson lambda with probability 1 minus p, would this be a tough problem? Yes, no, maybe. Remember, maybe is the right answer. So over here, if this was -1 and Poisson lambda, what is the difference between this being -1 versus 0? 0 makes it interesting, -1 makes it uninteresting. What happens when I set this equal to 0 versus -1? Sorry?
Both the cases for second situation also 0, there is some value.
Exactly. So the comment that being made is that if I give you this, if I tell you -1, then there is no possibility of getting a -1 from here. A Poisson random variable takes non-negative values. So for a Poisson random variable, probability that this random variable x is equal to k is lambda to the k e to the minus lambda over k factorial for k greater than equal to 0. That's what this probability mass function for a Poisson random variable is. So if I put this as -1, there is no way Poisson could have generated the -1. So if this was the problem, how do I get p? It's very easy, because I just count the number of times -1 showed up over the total number of experiments that I did. P is just that number divided by n. All the data points that were non-negative must have come from Poisson. From there I could have estimated the parameter lambda. Life was done. Now the issue is, as the gentleman back there commented, if I make this 0, then I have a problem that I don't know whether this 0 came from this branch or the 0 came from that branch. I don't know how it came. So it either came from here or it came from there. Question?
So what value of k do we get Poisson as 0?
K equal to 0.
No, but there still remains e raised to minus lambda, right?
What's that? No, but that's the probability, remember? The value that you get is k. So the random variable takes only non-negative values. It takes 0, 1, 2, 3, 4, 5, 6. So when you see the observation of the random variable, you don't get e to the minus lambda. That is the probability. What you see is 0, 1, 2, 3, 4, 5, 6 up to whatever. Right? So that's what the random events that are going to come from Poisson. When I say that x is a Poisson random variable, what I mean is that it has this probability mass function. I'm not saying x is equal to the probability mass function of Poisson lambda. Okay? So it takes non-negative values. From this branch it takes values 0, 1, 2, 3, 4. If I see a 1, I am sure it came from here. If I see a 0, then I don't know whether it came from there or there. Okay? And that's what basically is the missing part. I don't really know which side it came from. The moment I know which piece it came from, my life is easy. If I tell you that out of the m zeros that you saw, some, let's say, m1 came from here and m2 came from there, then again my life is easy, because now I'll know exactly what to do. This m1 will give me an estimate of p. That m2 I can plug it in over here and get an estimate of lambda. So basically the problem now is to take the zeros and split them into two halves, one that came from this side and another one that came from that side. Alright? And if you remember, if you go back to one of the examples that we worked out yesterday, there was x1, x2, x3, x4, and the problem was that this guy had a y1 and y2. y1 plus y2 was equal to x1. I didn't know how many times y1 came, how many times y2 came, and the moment I knew one of those, my life was easy. I could do a complete likelihood. All right? So this is sort of the same thing. I see number of zeros, I don't know whether it came from here or there. So this problem was sort of a warm-up problem so that you could directly use what was there in the notes to solve this problem. Okay, so let's go step by step to sort of understand what's going on. So the first thing that I asked you to do was to write the likelihood of the data. So the data that was given to you was, let's call it x, which is, first was number of xi's equal to 0, number of xi's equal to 1, and I think what was the largest number that was given to you? 6, 7, some such? 6. So number of xi's equal to 6. That's the data, because it turns out that it will be easier for us to write it that way rather than anywhere. Okay, so now let's try to start off from this. What is the probability that x is equal to 0? From this particular model, what is the probability that x is equal to 0? If this is my generating model and that's my random variable x, what is the probability that I see x is equal to 0? No? No, it's not p. P plus? P plus what? Yeah, but let's now you're in the position of telling me exactly what that answer is rather than telling me the formula. So what is the exact? So it's p plus what? Sorry? E to the minus lambda. Is that correct? Yes? Remember, the right answer is always maybe. And whenever I tell you that it's maybe, it's an indication this is not right. What is missing?
1 minus p.
1 minus p. Perfect. You need to have a 1 minus p here. Why? Because in order to generate a 0, there are two possibilities of generating a 0. One possibility is with probability p you went here, in which case you generate a 0 with probability 1. That's what p times 1 is. So with probability p you landed yourself here, and with probability 1 you picked up a 0. Perfect. With probability 1 minus p you came here, and now you picked a Poisson random variable. And what is the probability that a Poisson random variable is equal to 0? E to the minus lambda. Perfect. What about probability of x is equal to k for k greater than equal to 1? What will be the probability of x is equal to k for k greater than equal to 1? Can we get that from here? No. We'll get only there. So first I have to come land myself here. And that happens with what? With probability 1 minus p. And once I've landed here, what is the probability of getting k from a Poisson random variable? Lambda to the power k e to the minus lambda divided by k factorial. All right? Perfect. Now, what is the likelihood of the data now? So the likelihood of data given p and lambda is going to be the log. I want to look at the log likelihood. So it's the log of product of I going from 1 through some n probability that xi is equal to the probability of xi given p and lambda. Right, and how would we write this out? So now there are two things. This is the data that has been given where you have counted the number of zeros and ones. So if I write it this way, what would be the log likelihood, or what is this probability? How would I write this probability? So if xi is equal to 0, I will write this probability. So this you will end up writing is this is basically the summation of j going from 1 through some number n, which is the largest number that I saw. The number of xi's equal to j, actually j going from 0, times the log of the probability that x is equal to j given p and lambda. In this product, what's going to happen is this product, you will look at what is the probability x is equal to j and count up the number of times x is equal to j. That will become this. In this there will be a power of that. When I take the log of that, that power will come down here. Everybody see what is going on here? This is going to, you will count, in this product, you will have a number of times that x is equal to 0, 1, 2, 3, 4, 5, 6, so on. And when you write that product, that will be to the power of so many times, and that so many times just comes down here. Okay? So if we expand this for our story, this will be x0. Sorry, question? Good. Log p plus 1 minus p e to the minus lambda. And here I'm referring to x0 from here. So this is my x0, x1 to xn, let's say. And n is equal to 6 in our case. Right, so that's for the first one. Plus summation of j going from 1 through n of xj log 1 minus p e to the minus lambda, lambda to the k over k factorial. So that's the first part where I was just telling you what to do in terms of if you didn't want to use EM, this would have been the log likelihood. And you could have optimized this. So the first direct method would have been simply to say max over p lying in 0, 1, lambda greater than equal to 0 of L x p lambda. And that's the function. The down here, that's the function of p and lambda. You can just maximize that, and we will see a MATLAB, not a MATLAB, but Python code, which will do it for that coin problem. Okay? Everybody good so far? Okay. Now let's think about using EM for this problem. And how would I do that? I need to figure out what is the missing data. So what is the missing data here? What is latent? What was missing? We already had a discussion of this.
X equal to 0.
No, not really x equal to 0. That's not clear, right? Because x equal to 0 is not missing. There's something else that's missing. X equal to 0 was counted. It's right here. The number of times x was equal to 0. But that's not what was missing. Sorry? Exactly. So you don't, the x turned out to be a summation. The number of times I counted x is equal to 0 here. A few of those times came from here, and a few of those times came from there. I don't know which one of them came from these two. So let's define the missing data y to be equal to the number of times xi equals 0 came from first branch. I am not being very correct here, but you know what I mean. What I meant is that out of this x0, some portion came from the first piece, some other portion came from the second piece. All right? Okay. Now suppose my data z is going to be the old values, or let's say little x and y0. Let's call this, let's leave it as y, it doesn't matter. So this vector of all the counts, and then I'm additionally giving you this count y. That is, out of these x0, y of them came from the first piece, and x0 minus y came from the second piece. All right? So what will be my likelihood in that case? Not the log likelihood, but let's say I just want to go with likelihood. What is the likelihood? Which is basically this term. What is the probability of the data? Now my data consists of x and y given p and lambda. Suppose I tell you p and lambda, I gave you x and y, what will be the new likelihood look like? All of these guys, where did it go? These guys won't change. But what will happen to this guy? How would I think? Now if I give you the extra element that y of them came from the first piece and x0 minus y came from the second piece, how would you write it out? Sorry? What is the probability of seeing that data now? Go ahead. Well, I'm not talking about, I just want to do it the likelihood, not the log likelihood. So I need products. So it will be a product of what? Let's start let's start step by step. What is the probability I see y zeros coming from the first branch? What is the probability that I see y zeros coming from the first branch? P? Py? P to the power y, p plus y, p to the power y, because each of them are independent events. There are y of zeros came from the first piece. Each probability of seeing one of those was p, and therefore you will get p to the power y. Perfect. So there will be first piece will be this likelihood L will be p to the power y. And what about the remaining x zeros? What is the probability of seeing the remaining x zeros? 1 minus p e to the minus lambda whole to the power x0 minus y. Everybody get this? Because now I know what y was, I know how many came from this side and how many came from that side, right? And then what about the rest of the guys? It's going to be product of j greater than equal to 1, 1 minus p e to the minus lambda, lambda to the j over stupid j factorial, j factorial the whole to the power xj, because for them I don't have any confusion, and therefore the log likelihood L, little l, will turn out to be y log p plus, from here you'll get x0 minus y log 1 minus p e to the minus y e to the minus lambda, plus from here you'll get xj summation j greater than equal to 1 xj log 1 minus p e to the minus lambda, lambda to the j over j factorial. Right? Everybody see what's going on over here? And now let's just simplify this. Let's pick all the 1 minus p's and put them together, all the e to the minus lambdas, put them all in, all the lambda terms, put them in one, all the p terms, put them in the other, and then let's see where we go. Right? So from here going forward, little l, is going to be y log p plus, and now you're going to help me because my arithmetic is not very strong, x0 minus y log 1 minus p, or rather I'm going to take the 1 minus p common because that's going to help me in a bit. Plus, I get a bunch of them from here, j greater than or equal to 1 of xj log 1 minus p. Hopefully no errors have been made. So those are the terms that involve p, and then there will be a term that involves lambda. So let's put them together. You will get from here x0 minus y e to the minus lambda, you'll get lambda, or rather let's put the lambda terms also common. And from over here you'll also get all the terms from there. You'll get plus summation of j going greater than or equal to 1 of xj. Everybody good so far? All the lambda terms, this is basically coming from the e to the minus lambda term. The log of e to the minus lambda will give me lambda, x0 minus y and xj's, right? And now the leftover part is this guy over here, and from there you'll get plus summation of j going to be greater than or equal to 1 of j times xj log lambda. Okay, so that's this part, lambda to the power j. If you take log of lambda to the power j, the j comes down and you get summation of j greater than or equal to 1 j times xj log lambda. Perfect. Now why did I ignore this j factorial term? It's a constant, doesn't affect me in any way. I'm after p and lambda. Why do I keep track of unnecessary constants that are anyway complicated? Log of j factorial is not a well defined, it's not very easy, but I don't really care. Okay, perfect. Now this is my log likelihood. I'm pretending that I have the data. So if I have the data, what is the optimum value of p star? What should be the optimum value of p star? Looking at that, remember, this is of the form log y times log p something times log 1 minus p. So y divided by, what should be the summation of these? It's simply j greater than or equal to 0 xj, the total number of points that you have generated. But this is what we thought right in the beginning, right? If I knew exactly how much data came from the first piece, I know what the p star should have been. What about for lambda? I have to take the derivative. So basically I take the derivative of this guy and I get minus summation of j greater than or equal to 0 xj minus y. That's just this part simplified. From that part I get plus summation of j xj divided by lambda. This is j, let's just make it j greater than or equal to 0 so that I don't have to keep track of two different things. And when j is equal to 0, it doesn't give me anything different. I don't want to keep track of j greater than 1 and j greater than 0. Life is complicated as it is. So this must be equal to 0. So you get lambda star is equal to summation of j greater than or equal to 0 j times xj divided by summation j greater than or equal to 0 xj minus lambda. Not minus lambda, what am I talking about? Minus y. Everybody see what's going on? Okay. So if I knew what y was, life is easy. This is what I want to do. Now, I don't know what y was. So how do I fix this problem? So let's remove this part. I'll need this again. So I don't know what y is. So how do I define my q function? Q of new parameter given the old parameter. So let's say theta k. Theta k is the old parameter, and the theta in this particular case is going to be p and lambda. That's what I'm after. And what was this? Remember, this was given to be the expectation of the likelihood of the full data, which is x and y, conditioned on x and the old parameter of theta k. This is what the definition was. I don't know what the missing data is, so I'm just going to take the expectation of that missing data with respect to whatever information that I have. So if I stare at this function, which is basically the log likelihood, so this expression here is L of x and y. So the missing part, if I take the expectation, I just basically have to compute the expectation of y. Nothing else. Everything else is the same. I just need to compute the expectation of y. And wherever I have y sitting, I just have to replace that by the expectation of y. That's what I have to compute. And my calculations will be done at that point. Right? Does everybody get what I'm saying? I just have to compute the expectation, and at that point I'm done. So what is the expectation of y? What is the expectation of y given the x values that I have, which is that vector, and given the current values of the parameters pk and lambda k. I know the parameters so far, and I want to be able to estimate what would y be. So I already know this probability pk. Pretend that you know it, because this is the parameter that you're believing is true. Lambda k also is the parameter for this guy, and you believe that that's also true. Under that circumstance, I need to be able to figure out what y is. So how do I set this problem up? What is it that exactly that is happening? The total count is x0. This is the only information that I want. Some of those counts came from probability pk. Some of those counts came from probability. So I have x0 that I want to split into y and x0 minus y. This guy has probability pk. This guy has probability 1 minus pk e to the minus lambda k. Right? This would have been chosen with probability pk. That would have been chosen with this probability. So if I want to take what is the expected value of y, what will that be? Sorry? No, that is the so would be what? No, I just want the expectation of y. I don't want to take the expectation of x0 minus y. So what would that be? What proportion of these zeros would have, these x0s would have come from the first piece? This would be equal to pk times what? Times x0, perfect. That's it? You think that's enough? That's not quite right. Divided by what? Total probability. Perfect. Pk plus 1 minus pk e to the minus lambda k. So it would have come from two different proportions. Either these guys are coming with probability pk, those guys are coming with probability 1 minus pk times that. So the proportion of x0 is basically the proportion of x0, sorry, y is the proportion of x0s that came with that probability. So it's basically the ratio of that probability times x0 divided by the sum. I'm done. My EM algorithm is ready. So the EM algorithm basically says, I have that formula over there, pk plus 1, or let's define it correctly. So let's say the expectation of y given x and theta k is going to be pk x0 divided by pk plus 1 minus pk e to the minus lambda k. My new value pk plus 1 is going to be expected value of y. Let's call this, just instead of writing it again and again, I'm just going to call that y bar. It's going to be y bar divided by summation of j greater than equal to 0 xj, and lambda k plus 1 is going to be equal to, again, summation of j greater than equal to 0 jxj divided by summation of j greater than equal to 0 xj minus y bar. Everybody good? The story is actually very simple in EM. I don't want you to think about EM as being some dramatically difficult object. All you do is pretend that you have the data, write out the log likelihood, figure out what the update parameters are going to look like, and then wherever you don't have what you want, you don't have a y, just replace them by the expected value. And that's it. You're done. So this part, for those of you who are technically minded, this part is the E step, because you're actually taking the expectation of something, the missing parameters under the information that you have, and this guy is known as the M step, because you're optimizing over the parameters that you're going to do. So once we are done with all the written part, I'm going to go back and show you how things are done on Python, and it's very easily we can compute this thing. Questions? Good? All right, perfect. Now let's go to the second question. The second question is actually something starting to get practical. And this problem, the second problem, is a reliability problem. Happens a lot. It happens actually in many different contexts. It happens actually in reliability. It happens in also e-commerce, where you're trying to figure out your customer is there. They are interacting with you over a certain period, and then your period just finishes, and then you need to figure out what to do. Okay, so here's the story. I've got a random variable z, so this is problem 2. I've got a random variable z which lives, which has a lifetime, which is distributed according to some density f of z given theta. And I'm pretending that this is the lifetime of something. Let's say maybe lifetime of a machine. So you turn the machine on, and the machine crashes with that density. So the probability that it will crash at point z at some time in the future is given by f of z given theta. Okay? And then I have a time period, what did I call this over there? C. So I have an inspection period C. And what I've done is I have put n different machines. I prepared n different machines to start with, and here's my time. Here's my time C. The first machine dies somewhere here, the second machine dies there, the third machine dies there, fourth kind of doesn't die. The fifth dies, the sixth dies, seventh doesn't die. Now that's the story, because it actually dies somewhere over there. This guy dies somewhere over here. But I stopped looking at the machines over here. Okay? And so that's what I observe. So this is my x. That's the context of the problem. I observe my x's, and let's say because I have observed things, I'm going to reorder things, and the way the data that was given to you was x is equal, or xi is equal to zi for I going 1, 2 up through m, and it's equal to c for I greater than equal to m plus 1. So I'm observing this machine. I stop observing at time c, and at that point I don't know what to do because I don't have any more data. Right? And what do I have? What do I want to estimate out of this? I want to estimate this parameter theta. I want to estimate theta. So theta, let's say, is a lifetime of a machine. I want to understand how, so maybe at the end of this experiment, what I want to do is how often should I go and send a repairman to observe my machine. So this is the probability with which this machine dies. And so if I know this parameter theta, then I can sort of schedule my maintenance based on that. Now the same story can be done in an e-commerce setting, and one of my colleagues has actually worked on this problem. These are different customers that have interacted with your website, and all of these guys converted, meaning either they bought something from you or they said they're not interested. The story finished for them. These guys, you stopped observing them. And what you want to now figure out is how quickly should you be interacting with your customers? What should be the rate at which you should be interacting? Because that will depend on the rate at which they give up on you. So essentially here the machine dying means that they just stopped talking to you. They got bored. And so you need to interact with them before they get bored. So that's another context in which the same thing shows up. All right, good. Now let's try to see, and I want to estimate this theta now. I think in the problem I tell you to write the same thing, blah, 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 blah. Let's try it along the, well, let's not worry about it because we will try to figure out, we want to do EM, so we directly go to EM. The first part, you can look it up in the solutions, it's there. So let's say that the missing data is, suppose I had all the complete data. Complete data in this case would have been xi is equal to zi for I going from 1 through m, and also some yi, which is the missing part for I going from m plus 1 through n. And this yi is nothing but equal to their corresponding zi. I'm just going to write it that way because I'm keeping it consistent with what was there. Yi is the missing data. So what is the likelihood of this thing? What is the log likelihood of the full data? Let's what did I use in the solutions? I just want to make sure that I'm consistent with that notation. Yeah, okay. Zi, xi, and yi, which is the missing data. So what is the log likelihood of the full data? It's basically the summation of I going from 1 through n, the total number of data points, the log of f or up to mxi given theta, plus the summation of I going from m plus 1 through n, log of f of yi given theta. There's a bracket missing. Okay, so that's what the complete log likelihood is. Okay, how do I optimize it? If you give me the density, I can optimize it. So at the very end, there was a density given to you. So let's use that density. Suppose somebody gives me that this density is theta e to the minus theta z for z greater than or equal to 0. Suppose that's the density. What kind of a density is that?
Exponential.
Perfect, exponential. So let's plug that in there. I going from 1 through n log e to the log theta e to the minus theta xi plus summation of I going from 1 through n log theta e to the minus theta yi. Right? Separate it out. So you get n, this is up to m. So n log theta, that's the first term that you get. This is theta from here, theta from there, minus theta summation of I going from 1 through mxi plus the summation of I going from m plus 1 through n yi. These are the missing part. And so theta star, which is the optimum theta, is very simple. It's take the derivative. Oh, let's just do it in 2 steps then. Take the derivative, you get n over theta. Theta star is equal to n divided by summation of I going from 1 through m of xi plus summation of I going from m plus 1 through n yi. Is just take the derivative and set it equal to 0. You'll get that answer. Okay. Now the problem is I don't know this guy. So what would be my EM estimate? Just so we will figure out how to do the EM estimate, but what will be my theta EM? Now that you've seen lots and lots of examples of this, how would I construct my theta EM? The n will remain the same. These guys I know, so they'll remain the same, and these guys that I don't know, what do I do with them? Perfect, the expected value plus the summation of I going from m plus 1 through n, the expected value of yi given the data that I have seen and given the parameters that I have, which is theta. Right? That's what, so the new, rather the iteration would be theta k plus 1, the new value will be theta k there. Right? I don't know, I mean this is, by the way, something, if you put it this way, this is just like an iterative optimization problem. Really what I'm looking for is a fixed point. I'm looking for a fixed point where this is true. Right? I should, if I take the expectation with correct theta, I would get that theta back. And when you have a problem like this where you're trying to solve this equation, this nonlinear equation, one way to solve these nonlinear equations is actually start an iterator. You set theta k and theta k plus 1. And then you keep iterating until you converge. And because of certain special properties of EM, which has to do with this log likelihood continuously going up, if you know that the log likelihood is bounded, you will stop. Okay? By just a bounded convergence theorem, it will give you the answer. Okay? So in order to finish my EM story, what is left? I need to just compute that expected value. And that's going to be a little bit of a tricky story, and let's try to figure out how to do that expected value, and once we know what that expected value is, my entire story is over. In the in the assignment I'm asking you to do it for general. I will just do it for the exponential because it'll give you the idea. For the general one, just look at what's there in the solutions. More algebra, nothing new, no new ideas. So what I'm looking for now is the expected value of yi given x and theta. That's what I'm trying to compute. And once I have that, I have an iteration to go. So what happens, what is this expected value? This means that I got curtailed. So basically the question being asked to me is that I have an observation, take this observation, it got chopped at C. And now I've been asked is that if I know that this observation was greater than or equal to C, what is its expected value? Like what is the expected value that if you observed something up to C and it did not die, what will happen in the future? Now for those of you who know something about stochastic processes, memoryless property, so what is the expected value left over? Is what? So what is this expectation? So what is, I know that it didn't die up to point C, and we will do this in more gory detail in a moment, but for those of you who know some stochastic processes, you know about exponential distributions. The exponential distribution says that it has something called a memoryless property, which means that if I tell you that the exponential distribution was greater than C, then conditioned on this, it's another exponential. It doesn't, the distribution doesn't change. This information that I tell you that it has survived up to point C gives you no information about the future. For those of you who have done this is why you use this idea in a Markov chain. In a continuous time Markov chain, you use this because you don't have any information for the future about when it is going to die. The future and the past are independent. So given that all of that information, what is this? What is the expected value of the true lifetime given that the lifetime is greater than or equal to c, if the distribution is exponential?
1 by theta.
It's not 1 by theta.
Something.
X minus c.
Sorry?
X minus minus of x minus.
No. X is the observed lifetime. In this particular case, it's c, because after that I didn't observe it. yi minus x equals to, so you're right, yi minus x has an exponential distribution. It's e to the power minus theta. Therefore, the expected value of yi minus x is equal to 1 over theta. Therefore, expected value of yi is equal to x plus theta. So this expectation is c plus 1 over theta. Right? Because you lived up to c. Whatever is the leftover has a mean of 1 over theta. So therefore, this expectation is c plus 1 over theta. And so our problem is solved now. So this thing, theta k plus 1 is equal to n over summation of I going from 1 through m of xi plus the leftover guys, which is n minus m, and this is dotted with c plus 1 over theta, and this is theta k. Now iterate this, you'll get the answer. Okay, now let's consider this problem in a little bit more general way. Here we just used a prior information that I know that the exponential has this nice property. But suppose I didn't. Suppose this guy was just some f, not exponential, then how would I have done this? Then what I want is the conditional distribution of y given that y is greater than or equal to c. The density given that the survival was greater than or equal to c. I had something greater than or equal to c. So how do I write this out? What is the probability? How do I write this conditional distribution? This is going to be f of y divided by the probability that y is greater than or equal to little y. Okay? And what is this probability? According to this is y given theta. And how is this going to be represented? This is nothing but f of y given theta, the numerator is the same, 1 minus the CDF of y given theta. Right? Because the probability that y is greater than or equal to little y is nothing but the complementary CDF, which is 1 minus the CDF of y given theta. That's the density. Therefore, this integral will now just become the integral of y fy divided by 1 minus f y given theta dy from c to infinity. That's my expectation of y given x and theta. Some computation that has to be done. And in the solutions, you can sort of see how this computation ends up getting done. It's not very complicated. There's some integral that ends up happening. Punchline story, again, the formula remains the same. I want to estimate this theta. I have a bunch of missing data because the lifetimes are not known to me. I pretend that I had everything. That's where I started pretending that I have everything. When I start pretending that I have everything, I can write a formula for what the true parameters are going to be. Whatever I don't know, I take the expectation. And again, this is where the E step has happened, and this is where the M step has happened, because I have optimized my theta parameters to get that formula. My optimal theta star was done by maximizing this expression over theta. And this is the E step because wherever I didn't know what the parameter was, I took the expectation. Good? All right. Let's do the last problem and then we will do some things with showing you the codes. We can leave that there. Maybe I'll erase it from here. The last one is actually another technical, more of a technical problem. I can't show you that with data, but I will show you the codes with data for the other two, and we'll play around a little bit with the code to see whether our intuitions are right. So here the problem in problem number 3 is there is a random effects model, and this will introduce another trick. I won't fully do this because the full formula is a bit difficult. So let's look at this. So this is a random effects model. And the story of this problem is going to be the following. So I have different individuals. So I have I equals 1. How many did I say? I just want to be consistent with the notation over here. M individuals. And for each of these individuals, I took j equals 1, 2 up through some ni observations. Okay? Maybe different observations per individual. So for ith individual, I took ni different observations. What is the story? Let's say that I want to evaluate, to just give you a modeling exercise behind this, I have rolled out a new learning management system. I'm training a whole bunch of people in a company. I've opened out a learning management system, and I'm tweaking various parameters of it. I'm saying how long should they watch a particular video. I'm looking at whether I give them quizzes. I look at whether I periodically tell them to wake up because they actually may have gone to sleep while watching the video, and so on. So I have a bunch of different things. So I think that the progress that they have done, meaning for the ith customer, the jth observation has the following thing. For that customer, I might have given them different conditions. So that's xi transpose beta, meaning their reaction to each of those conditions that I gave is independent of the customer. There's a beta parameter that goes across people, and they react similarly to each of the conditions, but the particular condition I gave them might be different. For the ith one, I gave them quiz every 5 minutes. So there is a factor there. For the I plus 2th one, I gave them a quiz every 15 minutes. So there's a different one. So the beta of the 5 minute will be active for customer I. The beta of 15 minutes will be active for customer I plus 2. Plus, these guys have their own individual variations. People are different. So their learning ability are just innately different, perhaps. We don't know. So let's say that there is another parameter, alpha I, that just depends on the customer itself, and you have noise, epsilon ij, which is, for every observation there is a different noise. And let's assume that this noise is normally distributed with some standard deviation sigma squared. What are my observations? I look at that. That's all that I get. These are my observations. All right? Yes, question?
The transpose of xi.
I just made it a little bit easier. It's just that when I put them into a matrix, they will come. Basically, the way to think about it is for every one of them, there will be different conditions. So there will be a bunch of these are conditions, and there's a 1 or 0 sitting in here, which condition they had, and then beta also has the same structure, the same length. And therefore, it's better to me to think about transposes rather than row vectors. It just makes it life easy in terms of keeping track of what is happening. All right, so let's get rid of this. And what are my parameters that I'm after? Are beta and alpha. Excuse me, is it possible to turn on the AC? Is there a remote somewhere? Okay, so that's the parameter that I'm after and I want to estimate. Now, I want to make my life easy. I don't want to work too hard because the problem is that both alpha and beta are missing. So I want to be, and beta is the same across customer, alpha I is different per customer. So I want to think of this almost as a missing data problem. So what would be the right missing data to think about here? How would I think about something being missing that would make my life very easy? I see. From two different places. Okay. Perfect. Thank you so much. All right. So how do I think about missing data in this context? What if I think of something being given to me so that my rest of my problem becomes easy? If, for example, somebody gave me the alpha, what will be the leftover problem? What kind of a problem will be left over? The problem in estimating beta, what kind of a problem will that be? If I knew the alphas. If I knew the alpha, what would be the problem in beta? How would I estimate the beta, given that these are all normally distributed? Sorry? Simple regression, right? So if I knew the alpha, this random effect model just boils down to simple regression. I know lots of things about regression. I can do it very easily. So if I think of alpha as missing, and somebody gives me those alphas, then the leftover problem is trivial. So that's what I want to do. I want to be able to do the leftover problem trivially and try to figure out what is going to happen. So let's try that. So suppose the complete data set consists of Sij's and alpha i's for I and j. So this is the complete data set that I have. Somebody gave me the alphas, and my story will simply be, I will write the log likelihood for this. I will compute out what the optimal values of the betas are going to be, and then I don't know the alphas, so I'll replace them by the expected values. And then we'll see what happens with that. Okay. So let's write the log likelihood, and this one is going to be a little bit complicated, of the complete data given the parameter beta. That's the only thing that I'm trying to estimate now because alphas are known. Okay. So what is this log likelihood? It's the summation over all I, summation over all j, going to ni of Sij minus beta minus alpha I, no, not beta, xi transpose beta, squared with a minus 1 over 2 sigma squared. Right? This is basically because this is normally distributed. If you take the log of the distribution, you'll end up getting that. There's another, at least in the solution that I was giving there's another assumption that is made, that these are the same, but I also have an information that alpha I is distributed normal 0 nu squared. So I'm looking for this nu, and it's also distributed according to 0 nu. So you'll have another term here which is minus 1 over 2 nu squared of summation of I going from 1 through n of alpha I squared. The second piece is coming from the fact that each of the alpha i's are distributed according to nu. Okay. Right. Good. And what do I want to do there? Okay, good. Yeah. And so the parameters that I'm after are actually sigma squared and nu, or sigma and nu. These are the three parameters that I'm after. The distribution of the noise, the distribution of alphas, and beta, which is the parameter of that quantity. That's what I'm after. And I have assumed, also missing is alpha, which now I'm assuming that the missing data is alpha. So in this particular case, now the parameters that are left over are beta, nu, and sigma. Okay, let's fix on beta. The other things you can calculate from, you can figure it out in the solutions. So if I want to get the optimum beta, beta star, so I take the derivative of this and set it equal to 0. What will be the optimum beta in that particular case? So I take the derivative of this guy, dl d complete d beta. So from here I'll get 1 minus 1 over sigma squared, summation over I going from 1 through n, summation of j going from 1 through ni, Sij minus xi transpose beta minus alpha I, and the minus sign gets cancelled with that minus sign, xi. That's what it's actually not derivative because this is a vector, so this is basically the gradient with respect to beta. I'm just abusing notation. So that's what, and these are all the vectors xi's that I'm going to get. And we can set this up and figure out exactly how to trying to figure out what's the easiest way to do this. Have to set this and put it equal to 0. So if I do a little bit more algebra, you'll take the product of these two guys, you'll get the summation of I going from 1 through m, summation of j going from 1 through ni, Sij times xi, that should be this term, or let's say Sij minus alpha I, the whole thing times xi, and on the other side you'll have I going from 1 through m ni xi transpose whole thing beta. And this is going to come because of the fact that these are just common. You'll have ni terms coming from there, and this one we kept it already as it is. So that's what that is. Call this some matrix M. So beta turns out to be M inverse summation I going from 1 through n, j going from 1 through ni of Sij minus alpha I times xi. All right, so that's the optimum beta. It's just as it's a little bit, the algebra looks a little bit different, but it's really linear regression. Nothing else happened there. So now if I want to do my EM beta, what will I do? The M inverse remains the same. This I going from 1 through m, summation of j going from 1 through ni, Sij, and now what will change over here? The alpha, which I had assumed to be latent and known, instead of that I'm just going to put that as the expected value of alpha given the data and given the parameters times xi. That's it. That's the EM estimate. When I don't know what something is, I just take its expectation. Now let's try to figure out what that object is going to be. So what is the expected value of alpha given all the data that I have? So it's not S actually, it's X, S, because that's the data that I have, S and theta. This is an interesting trick. This will bring down an interesting trick which we will play with in a moment. So let's look at the conditional distribution of alpha given my observations and given all the other parameters theta. This is what I'm after. What is the conditional distribution of alpha given my current estimates for all the parameters? So this is what my theta is. and all my observations S. So I'm going to say that this is proportional to, this is a trick that we've used a lot of times, which is equal to this is the trick that we have played many times. I don't know this conditional distribution, so using Bayes' rule, I write it the other way around. What is this guy? This guy is nothing but normal 0 nu squared. Or let me write it in a density form. This is 1 over 2 pi nu squared, or square root, e to the minus alpha over 2 nu squared. Because I'm assuming that each of the alphas is distributed according to the normal distribution, so I get that this piece, given the parameters, it's just that. What is this one? I already know what betas are, so this piece is going to be e to the minus, or product, let's say alpha I is after what I'm after. This is going to be the product of j going from 1 through ni, 1 over 2 pi sigma squared, square root, e to the minus Sij minus alpha minus xi transpose beta minus alpha the whole squared over 2 sigma squared. It's basically normally distributed according to that. Now that looks like a messy distribution. Just let's take the log of that, and that's there in the solution as well, and I'll tell you why this will be interesting. Suppose I take the log of that, and let's not worry about the constants, so you will get minus alpha squared over 2 nu squared from here, from this term, plus you will get the summation of j going from 1 through ni Sij minus xi transpose beta minus alpha bear with me, this will start to make sense a little bit more, plus some constant which I've ignored. And so this, if you take a log of that, you'll get that expression. So if you look at this expression, what can you tell me about alpha? What is the distribution of alpha I? What is that posterior distribution of alpha I? And my claim is that if you know this, if you look at the form of this, you should be able to tell me what the distribution is. Just by looking at that, and that's going to help me to figure out what to do. Somebody said the right answer. Normal. Why normal? Oh, but if exponential doesn't necessarily be normal, right? But there's a special property of that thing which will make it normal. Your answer is right, that it's normal. But how do I know that it's normal? What's that? No, the prior is normal. Why should the posterior be normal? Let's not think too much about it. Basically, if you open this up, what kind of a polynomial in alpha did you see here? Second degree polynomial, right? And that's and the power of the alpha squared will be minus 1 over 2 nu squared here, and from here it will be the summation of ni. It will be ni over 2. Sorry, this should be sigma squared. So it will be ni over 2 sigma squared from here, 1 over 2 nu squared from there with a negative sign in front. So the power in front of the alpha will be negative. I don't really care about the linear term and the constant term. That looks Gaussian. That's really a Gaussian distribution. So I'm done. So the alpha is now distributed according to normal some mu I and some other then variance gamma I squared. So how do I know what gamma I is from this calculation? How would I figure out what gamma i's is going to be from here? Is a quick way for me to figure out what gamma i's is without doing everything, without filling up everything? Look at the power of alpha squared. Here in the exponent, what will be the coefficient of the power of alpha squared? 1 over 2 gamma I squared. So that power 1 over 2 gamma I squared must equal the coefficient from here, which is must equal 1 over 2 nu squared plus ni over 2 sigma squared. So these cancel and you get the formula for gamma I. What about the mean? How do I figure out the mean? I take the linear term over here. What will be the contribution of the linear term? So I know that mu over gamma I squared should equal, the linear term from here would be summation of j going from 1 through ni of Sij minus xi transpose beta divided by sigma squared. And from there, once I know what gamma is, we can compute the mu from here. So you compute gamma, plug that in here, this will give me the mu. And once I know the mu, I stick that mu over here. And I'm done. So beta Em is going to be equal to M inverse, this junk, mu I, or the mu vector, xi. Repeat. And this one I don't have a code to show you, so most of it is just algebra. Why did I go through this algebra? Really to just come to this trick. Everything else is routine, but this is a trick. Yes? Which one? This one?
Second last to last.
This one and these two? So what I did was I now know that this distribution is normal. So if I know that the distribution is normal, then let's write out the log from this side. What should I erase? Maybe I can erase this. So I'm assuming that f of alpha is normal mu I gamma I squared. So the log of f of alpha will look like constant minus alpha I minus mu I squared over 2 gamma I squared. And if I expand that, I'll get C minus alpha I squared over 2 gamma I squared plus mu I alpha I over gamma I squared plus mu I squared, minus mu I squared over 2 gamma I squared. And that's what the expression is. So I'm going to take the second power of alpha and compare it with the second power of alpha on the right hand side of that expression. So from here I get 1 over gamma I squared or 2 gamma I squared, and from the other side I'll get 1 over 2 nu squared plus ni over 2 sigma squared. So that's how I end up getting. If I look at the power of alpha I from here, I'll get mu I over gamma I, and then I'll compare it with the power on the other side and I'll end up getting whatever I needed. Alright? Perfect. So let's just keep going for a little bit and then we'll take a break after I just show you all the solutions. And what I want to do now is just show you some Python code for the two problems, and I'm told that if I press this down, it should come down. Magic. Good. So this is basically the code from the first one. I've just defined two new variables. This is q, and if I know what q is, then the p new, the new value of p is nothing but x0 times that proportion. The proportion that the data came from the first half, which was x0 times p divided by the sum of the two probabilities, which is p plus 1 minus p times e to the power minus l. That's what P new is. If I know what that is, then the value of the L new is nothing but the summation of what is this? What is X times J? What I did was that I just created an array. Those are the arrays of X's. J is just an array of 0, 1, 2, 3, 4, 5 up to N. That's what capital J is. So when you look at this one is just summing JXJ, and in the denominator, here we go. Oh, but I don't have this. Hopefully this will start working. So that quantity over there is nothing but the new estimate for L. The code next one says that if the maximum of the new value of P and the new value of lambda happens to be less than tolerance, you come out of the loop. Otherwise, you set P and L to be equal to the new values. That's what this is. And then you append that to a theta list, which is the list of parameters, so that I can plot it later on. And then here we just plot the progress. So I created two different lines, one for P, which was the first component of theta, another for lambda, which is the second component of theta. I plotted it, and you end up getting this as the plot. Start from, so after about 2 iterations it converges to whatever is the values that it wants. And if I want to just quickly see what that comes out to be, oh, that's not the correct theta. The correct theta should have been here. You need to run this again. So that's approximately what I started that theta from 0.75.4, and it converges to about 0.615 and 1.037. This is, if you look at the solutions, that is the number that is approximately there. This is problem number 2 in the homework. Here I'm randomly generating the data. I have 1,000 data points. I assume that the mean of the exponential distribution is 20. Now in Python, the parameter that you have to give is the mean, whereas in the homework problem, the parameter that we defined was the rate. And so it's just 1 over the mean. But here I'm just generating data with a mean lifetime of 20. And we will play around. Here's the censoring value down there. This is the censored value. All I said was I set C to be equal to 1.1 times beta 0. We will play with this number in a moment to be able to see what happens. X, which is the actual value that I get to see, is the minimum of Z and C. If Z is less than C, you get to see the actual lifetime. If Z happens to be greater than C, then it gets censored at C. You don't see anything more than that. I put them in increasing order. I counted the number of y's that are less than C because that I needed for the calculation. And here's my iteration. Theta new is just nothing but N, which was the total number of data points, sum of the y's from 0 to m, because these are the true measurements, and n minus m times C plus 1 over theta. This is the leftover part. And if the iterates are different by more than tolerance, you continue. If they are not, do it. And then again, you plot it. And so I'm going to run this, and then what I want to do is play around with that thing and see if it makes sense. So here's what the estimation are. So the final estimation that it got, did I call it beta list or theta list? Theta list. Or beta. So that's what it estimated it. It started with beta equals 1, kept on going, and it computed the beta to be about 20. And the true beta 0, is 20. All right, good. Now let's play around this with a little bit. Suppose I tell you that I censored at the 0.5 level. So the censoring value, I dropped it from 1.1 times beta 0 to 0.5 times beta 0. What do you expect would happen to the estimate of beta by EM? Can you guess which direction it will go? Will it reduce, increase, or can't say? Magic answer, can't say. So think about the following situation. You have a mean lifetime that is 20, and you measured only up to 10, and then you're trying to estimate the beta by just looking at everything that did or did not die within 10. What do you expect it to do? Do you expect your estimates to be large? You expect your estimates to be small? And it should not matter. Small. But I'm going to argue the other direction. Remember, these things are exponentially distributed. They're memoryless. So whenever I stop, the leftover part is still exponential. So maybe it doesn't matter to me. So which direction will it go? So let's try it. Let's run it with 0.5 and see what happens. That's one of the good things about actually running it. It took a little bit more time, but it converged to pretty much the right answer. All right, so maybe everything is good. Let's be extreme. Let's make it to be 0.1. Okay. Now what happened? It's struggling. It went up to 16 and then died. It just stopped right there. Now the difference here is that had we done a true parameter estimation, that is true maximizing the log likelihood without going through this EM business, we would have gone a little bit more. But if you become very extreme, this memoryless property doesn't help me too much. It would help me a little bit. Let's try one more trick to see whether it makes any sense. Let's suppose we have 10,000 is a little too extreme. Let's make it more data points. Do you think that will make a difference? That it will come back to being the right estimate? If you have more data points, should it be better or worse? Now you get to choose before I hit the next return, because after that we know the answer. Better. Not really. In this particular case, what happened was that you are censoring the data so much that you really did not gain too much out of it. Why did I want to show you this code? Because I want to get you guys into thinking about data analytics as an experimental science. I don't want you to think of it as a math science. It is mathematics. We need mathematics to be able to write the correct code, but once you have the code, you can play around with it and see what things are happening. And that's one of the reasons I am pushing this idea to have a nice notebook. You can share the notebook. You can send it to a friend who can code for you and send it back. And it's very nice. You can embed code, you can embed data, you can embed plots all into the same notebook. And in fact, I don't go to that extreme because a lot of things that I teach are still very technical in nature, but there is a colleague of mine who teaches basically undergrad level data analytics, and he teaches it completely in a Python notebook. When at the beginning of the class, the students get a Python notebook and that's their notebook. All the homework is done there, all the classwork is done there, every story that you want to write, it's in there. And at the end of the class, you have the entire thing available to you as a notebook. So when you do things with, and again, there was a question about R. Now R notebook is available. You can call notebook in R. So I would really encourage you to think in terms of notebooks, because it really is a notebook. You can hand it over to somebody else. You can write a story there. For example, in this one up here, I tell you, so for example, this is just English. You can write down. There are choices for markdown over there. Markdown allows you to write text. Code allows you to, well, if you write it a code, it became garbage. I will make it back into markdown. And you can write whatever you like over there. But those of you who are used to writing LaTeX, I have embedded LaTeX in there as well. So it really is, it's really a living document. And one of the things that's so nice about it is that when somebody else gets them, they can actually run your code with different seeds, test it, do all kinds of things with it. Last bit before we go for our lunch break is I want to show you that other example. Sorry, question? Okay. This is This is the negative log, this was the negative log likelihood function when the coin identity is known. When the coin identity is not known, what you want to do is write the expression slightly differently, and the expression is just it's log of 1/2 of f of x given theta a plus 1/2 of f of x given theta b and xi, and this is a summation of I going from 1 through n. This is the log likelihood. So that's what is happening over here. I look at a binomial distribution with n trials with thetas. So when I say thetas, it's a vector of both theta a and theta b. So when you say thetas and PMFX, it will actually create a row vector where this is sitting there and that is sitting there. I take the sum of them and multiply by 0.5. I get exactly this expression. And I'm doing this for all x's. So now I have a vector of these expressions for all values of x. And then I take the sum of that, and that becomes the log likelihood, except that I want to give a negative likelihood, so I put a minus sign. And that becomes the function that I'm going to call. And if you run this function, it's somewhere over here somewhere, right, here go. It doesn't run. Why? Because I must not have done some crazy things here. So let's make sure, oh no, let's run this from the beginning, and now it converges and gives you the value of 0.48. So why is it giving me a value of 0.48? Because remember, I started this guy at 0.5. If I start this coin at 0.5, it's not able to differentiate at all. So let's try our other trick where I make this 0.49, and now it goes to 0.6 and 0. Now let's make it 0.3 and say, I don't know, 0.8. Now it goes to some other number. So it turns out that with trying to do this negative log likelihood with a combined one, in fact, is more unstable compared to the expectation maximization method. So the expectation maximization method in this case turns out to be a more robust method. It may not be the correct, always give you the correct answer, but it tends to be more robust. So that's another message that I wanted to give you from here. All right, so we'll take a break.